Okie dokie. All right, let's take a look at what things look like today here in our Buzz curriculum. Let's put this up on the screen. On our grade screen, as usual, for start, when we scroll down, we should have the first lesson done in Module 3. It's what we did last week, the greatest common factors, special products. We moved this back, and originally I'd planned on that for last week, but I said, nope, there was a lot to cover in this first lesson. So today we're covering these two. I've moved this one back. I've had to rearrange the rest of the schedule since that first lesson was so long. So we're going to look at factoring by grouping, which is a longer lesson, and then summing difference of cubes, which is pretty quick. So we're able to do both of these today. And then next week we'll get into graphing quadratics, which you already pretty familiar with, but we're going to look at completing the square, which will take a little bit of time. That's probably the trickiest part of this whole quadratics unit, is the completing the square part. So that'll be something to look forward to next week. Factoring by grouping 3.02. Let's start there. There it is. You will want some notes on this factoring by grouping unless you're very familiar with it already. But we're going to talk about how the discriminant can be used to determine the number of solutions for a trinomial in standard form. We're also going to look at what methods can be used to factor a 4-term polynomial. Probably don't see a 4-term polynomial very often, but we're going to today. And in what conditions can rewriting a trinomial as a 4-term polynomial allow for factoring by grouping? So looking at this tree, it's got the methods of factoring up the top, the different branches represent methods of factoring. And you've got this discriminant, b squared minus 4ac, as the trunk, which leads down to the roots of the solution. So the skill of factoring trinomials is like a tree. There are a couple of branches, like finding the greatest common factor, and special products, like we learned last week, like difference of squares, that works in special cases. However, the trunk of the tree holds it all together and leads to what type of solutions we can expect to have. So the trunk is called the discriminant. So the discriminant is a function using the coefficients of a polynomial that indicates the nature of the roots of that polynomial. A tree surgeon would examine the trunk to get a good idea what's happening in the roots of the tree, and mathematicians can examine the discriminant to determine what the roots are like. So the standard form of a trinomial, here's where we will start our notes right off the bat. So the standard form of a 3-term trinomial, tri is 3 terms, is ax squared plus bx plus c, where a and b are coefficients and c is just a constant number. So from this, we're going to talk a lot today about the discriminant. So the discriminant looks like this. And we'll put a line between there. B squared minus 4ac. And the discriminant is going to tell us a lot of information. So let's make a little place over here for our notes. So we're going to say if the discriminant equals. And there's going to be 4 different cases of what we're looking for. Okay, so I don't want to get too far ahead of our notes in here. So this does an example of how you do a discriminant right here. So let's write this example down of how we calculate a discriminant, and then we'll talk about what the solutions tell us. So here's an example on calculating this discriminant, because we've got A, B, and C in our standard form, which is where our A, B, and C come from that we're going to use in the discriminant. So when we look at this example, this is our A, this is our B, and this is our C. That's all we care about for the discriminant. So it's B squared. So that's 7 squared minus 4 times A times C. So calculating the discriminant would be 7 squared minus 4 times 2 times 6, or B squared minus 4 times A times C. So 7 squared is 49, 7 times 7, minus 4 times 2 is 8. 8 times 6 is 48. So in this case, the discriminant equals 1. Like, okay, the discriminant equals 1. What does that mean? Well, if we look here at our third page of the notes, we have 4 different possibilities on what the discriminant could equal. So let's talk about it. If the discriminant equals 1, I'm sorry, 0, not 1. I was just thinking of our example here. If it equals 0, no, if it equals 0, then there is one, let's call it one real solution. Okay, so if it's 0, the discriminant equals, and ours does not equal 0, ours equals 1. But if it equals 0, that would give us one real solution. So what's the next case? If it equals a perfect square integer, right? Perfect square integer. What is a perfect square integer? Well, if we think about what a perfect square is like 1 squared, 2 squared, 3 squared, 4 squared. These are all perfect square integers because we can square a number and get them. So 1, 4, 9, 16, 25, 36, 49. All of those numbers are perfect square integers. And if it's a perfect square integer, there are 2 real solutions. If it is an integer but not square, right? So maybe we got, this is a perfect square, right? 1 times 1 is 1. So this means this has 2 real solutions. We could factor this. It's factorable. I'm going to put that in parentheses, factorable. Because it has 2 real solutions, it's factorable. An integer that's not a square, let's say that this equaled 3. 3 is not a perfect square. Or if it equaled 11 or it equaled 20, something that's not a perfect square, that means we have 2 irrational solutions. Irrational, which means the solution is not going to be x equals 6. It may be x equals 3 plus the square root of 7 or something. Like it'll be a real solution. It just will be irrational, which generally means it's not factorable. And the last case, what if the discriminant is negative? It means 2 complex solutions, which complex means imaginary. 2 complex imaginary. So this is what the discriminant tells us. It'll tell us if our equation has 1 real solution, 2 real solutions, which means we can factor it, 2 irrational solutions, means we probably can't factor it, or 2 imaginary solutions, which means we definitely can't factor it, and we'll have to use the quadratic formula to find the answer. Okay, so this is what you would definitely need in your notes, what you want to know. And it's right here on the first page. It's in the first page here in Buzz. It's just that you got to use the little arrows to get over to it, but it's the third point here, that 0 is one rational solutions or real solutions. Positive perfect square, two rational solutions. A positive integer, but not a perfect square, two irrational solutions. And if it's negative, two complex solutions, which means it's imaginary. So we're going to put some examples of this and learn more about what we're talking about with there, because it's like, okay, I see what you got on your chart there, Mr. Brock, but what does that mean? Some examples will help clear this up. How does this affect perfect square trinomials that we looked at last week? Like if you have b plus 2 times b plus 2, that's b plus 2 squared, and that'll give you a perfect square trinomial. So if we did the discriminant of a perfect square trinomial, like x squared plus 8x plus 16 meets the pattern to be a perfect square trinomial. If you found a discriminant, the discriminant would always be 0 on a perfect square trinomial, which would mean there is one rational solution. But when you factor that, it's x plus 4 times x plus 4. So it's x plus 4 squared. We know there's two solutions, but they're identical. They're both negative 4. If it's x plus 4 times x plus 4, then your solution is x equals negative 4. There's two of them, but they're the exact same number. So we count as one real solution. It's only going to cross, it's only going to hit the x-axis at negative 4. There's one unique solution. It just has a multiplicity of two. Multiplicity, but there's only one solution. All right, let's get on to the next page and talk about factoring by grouping. 4-term polynomials. Starting with 4 term, that's a little different. So what's the following pairs of binomials being multiplied? So if we have these binomials here, t plus 3 times t plus 11. And maybe let's put this in our notes. I think that'd be useful. So if we have two binomials and we're going to multiply them together, the first thing we do is we multiply t times the t, right? The distribution method, t times the first term, t squared. And then we'll take t times the second term, 11. So that's 11t. Then we have to take, let's see, we're through with this one. We've multiplied it by everything in this parentheses. Now let's take the 3 and multiply it by the first term. And the 3 by the 11. 3 times 11 is 33. So this is what we end up with. We end up with 4 terms. In this case, when we multiply these together and got 4 terms, we see that we have the middle terms are like terms. They're both just t terms. They both have coefficients and they're both t's. So we can combine those, 11 plus 3, and have 14t plus 33. So that's what our polynomial is, our trinomial. And we're going to look at some where we have a 4 term that they're not all the same. But starting out, let's just remember how that works. So when you multiply those together, you got t squared, you got 11t, you got 3t, and you got 33. And then you got those middle terms you can combine and be 14t. So here's another one, t plus 3, s plus 11. We've changed it to 2 different variables. So we do the same multiplication. T times s is st. T times 11 is 11t. Now when we distribute the 3, we've got plus 3s and 33. So this is a little different because we changed it to 2 different variables. The second binomial has a different variable. So now when we look at this, there are no like terms. We cannot combine anything. So we end up with just st plus 11t plus 3s plus 33. But if I gave you this first, you'd probably think that's not factorable, but obviously it is, because there's the 2 factors that we use to create it. So what's different about the outcomes from group 1 and group 2? Well, the first group, the middle terms combined. In the second group, they could not be combined, so it left a 4-term polynomial. So we're going to use what we saw in the animation to try working backwards to find the two sets of binomials that would multiply together to be this. Oh, that's a good one. So let me write this down. All right, so if we had that and we're trying to work backwards, this is how factoring by grouping works. Because if we look at this, we're like, how in the world do you factor that? There's four terms and there's nothing in common. I can't factor out a 2. I can't factor out an x because this doesn't have an x. I can't factor out a y because these two terms don't have a y. How do we factor that? Obviously, it's factorable somehow because we can build one by multiplying two binomials together. We just saw that when you change this to a different variable. This is how this works. If we group this, I'm going to group those first two terms by putting parentheses. And then I'm going to take the second two terms by putting parentheses. And now I'm just going to look at it part of the polynomial at a time. If I just look at this term, I can factor out an x because both of these terms have an x. So if I factor an x out of that, x squared divided by x is x, xy divided by x is just y. So I can factor out part of it. Then if I look at this, I've got negative 2x minus 2y. I can factor out negative 2. Negative 2 out of negative 2x just leaves x. Negative 2 out of negative 2y just leaves y. Now I have two terms, and both of them, I'm going to highlight this, both of them have an x plus y. So I've got x times x plus y minus 2 times x plus y. So if I factor out x plus y, what's left here is just x. What's left here is just negative 2. So these are the factors of this. You're like, seriously, Mr. Brock? Those are really the factors because let's multiply them back together. X times x is x squared. X times negative 2 is negative 2x. Y times x is generally put the alphabetical order xy, and y times negative 2 is negative 2y. This is the same as what we started with. We just switched those two terms, which is fine. You can write them in any order. But this is x squared plus xy minus 2x minus 2y, x squared plus xy minus 2x minus 2y. If it makes you uncomfortable, you can go ahead and write it again in the same order. But this is the same as what we started. So that is the two terms. This is how we factor it. By grouping them, just pulling out things they have in common. Factoring by grouping. So that's what we're looking at in this lesson, is factoring by grouping, because it's very useful. Because otherwise, when we look at that, how in the world can you even factor something like that? Well, we can do it factoring by grouping, because pairs of terms are grouped together to be able to factor a piece at a time. So that's where they have the original x squared plus xy minus 2x minus 2y. Okay, let's look at factoring this one. C squared d minus 4cd plus 4c minus 16. Looking at that, you're thinking, "Ooh, that looks like a mess as well." But it is factorable with this method we're learning. You may have seen factoring by grouping before, and this would be a good review for you. But if you haven't seen it, this is good to learn.
Check each term in the original polynomial for a greatest common factor before trying to factor it any further. The first term has a coefficient of 1, so this polynomial does not have a numerical GCF greater than 1. The last term doesn't have any variables, so a variable cannot be factored from each term. Therefore, a GCF will not be factored. When factoring by grouping, look at the expression in pieces to make it easier to find the common binomials hidden within. Group the four terms into pairs, the first two terms and the last two terms. The next step is to factor the GCF from each group. First, factor the GCF from the first pair of terms. C squared d and negative 4cd have 1c and 1d in common, so the greatest common factor is cd. When cd is factored out, you're left with c minus 4. Now, factor the GCF from the second pair of terms. 4c and negative 16 have a GCF of 4. When 4 is factored out, you're left with c minus 4. You're finished with this step. The next step is to factor the common binomial from each group. Notice that the binomials in parentheses are exactly the same. c minus 4 is common to both terms. Therefore, it is a GCF, which may be factored from each term, leaving the other factor, cd plus 4. So the final factored solution is c minus 4 times cd plus 4. But you're not quite done yet. Don't forget to check the factors by distributing. If the product of these factors matches the original polynomial, they are correct. c times cd is c squared d. c times positive 4 is positive 4c. Negative 4 times cd is negative 4cd. And negative 4 times positive 4 is negative 16. You can see that the terms of the product are not in the same order as the original polynomial. But these terms can be rearranged. Just don't forget to take the sign with each term, and that's it.
And that's it. So that's another example, just very similar to the one we did on paper, but it is factorable into these two binomials. All right, let's see what's on the next page, page 3. Okay, let's look at some more 4-term polynomials that can be factored by grouping. You'll see in the next example that a GCF can be factored out initially from all terms. So let's watch out for this. So let me put this one in our notes. All right, got this one written down. So if we look at this, step 1 in factoring is always greatest common factor. Is there something we can pull out before we start? That's always step 1, no matter what method we're using to factor. When we look at this, we see 30, 20, 15, and 10. And these are negative, but they're still, all of those we recognize right away are divisible by 5. C third, C squared, C, no variable at all. So 5 is the only thing we can factor out. But doing that first is going to make this a lot simpler. So 30 divided by 5 is 6. So we have 6c to the third minus 20 divided by 5 is 4c squared. 15 divided by 5 is 3c, and 10 divided by 5 is 2. So now we've simplified it down to 6c to the third minus 4c squared minus 3c plus 2, all times 5. So let's factor this now by grouping. So I can put parentheses right there to put the first 2 and the second 2. And let's see what we can pull out. So we've got a 5 out front still. We can't forget that. That's outside there. 6c to the third minus 4c squared. Well, 6 and 4 both have a 2 in common. And c to the third and c squared both have a c squared. So I can pull 2c squared out of this binomial. 6c to the third divided by 2c squared would just be 3c. Negative 4c squared divided by 2c squared, negative 2. And there's no c left because c squared divided by c squared is just 1. So the first step, we're able to factor out this, just leave c 3c minus 2. If we look at this, we're like, well, there's nothing in common. But here's the key about factoring by grouping. I want to get the same binomial that I can factor out, right? In this example, we have the same binomial. Can we make this a 3c minus 2? We can if we factor out a negative 1, which just changes the sign, right? So this is 3c instead of positive 2, it's minus 2. So we've got a 3c minus 2 in both terms by factoring out a negative 1, which means this can now be factored to the front. So you got 5 times 3c minus 2. And when you factor this out of both of those, that leaves this 2c squared minus 1. And that's it. This is the factors of this. We can factor this to be 5 times 3c minus 2 times 2c squared minus 1. Marvelous. That's as simplified as it gets. You might look at this right away and go, oh, is this difference of squares? Because 1 is a square and c squared is a square. Yeah, but the 2 is not a square. If this was 4c squared minus 1, we would additionally factor this down using the difference of squares that we learned last week. But the 2 is not a square number. So this is as simple as we can simplify that. That's as far as factored as it gets right there. So they'll go through the steps here if you want to look at that. They'll find the common factors 5 times 3c minus 2 times 2c squared minus 1. If you need to look at it again through their example and through the way they step through it, but that's the same thing. CD squared plus 7d plus 8c minus 16. Factor the greatest common factor. In this case, there's not one because there's no coefficient out here, so we don't have to worry about the 7, 8, and 16. There's no variable down here, so we don't have to worry about the c or d being factored out. Again, you group them, the first two and the second two, factor out what you can at the first one, which is just a d. The second one, you can factor out an 8. So you end up with that cd plus 7. Oh, this one. Oh, yeah. Gotcha. Let's put this in our notes because this is important. This is important. All right. I'm going to go back and start this over just because this will show you what happens sometimes when we can't get that common binomial. So we'll put this in our notes. This first binomial, when we group that, we can pull out a d, like they showed us on the buzz lesson, which leaves cd plus 7 when you pull a d out of both those terms. This one, 8c minus 16, we can pull out an 8, which leaves with c minus 2. Look, these are not the same. We cannot factor. This is done. This is all we can do, which means this is a prime polynomial. Prime polynomials can't be factored. These are not the factors because these are being added together. Factors multiply together to equal the original. We rearranged it by trying to factor some of it out, but it's a prime polynomial. Just like, 13 is a prime number, can't be factored. It's the same to think about a prime number. Prime numbers can't be factored. Prime polynomials can't be factored. It's prime. That's it. So it works the same way when you talk about a prime polynomial. It's just like a prime number. It's in its simplest form. It cannot be factored further. So when you factor the common binomials, there's nothing. They don't exist. So this polynomial is prime. Okay. Will there be cases where common binomials do not exist, but the polynomial is not prime? Yes. So false primes. Let's look at a false prime example here in there. Actually, could be a false prime because of a human error. You might think it's a prime number when it's not. Like we have xy plus 4y minus 5x minus 20. It's one of those cases where you factor out y and you get x plus 4. And here you say, well, I can factor out a 5. And that'll leave negative x minus 4. And you're like, okay, well, this must be prime because they're not the same. Well, that's a human error. If you would have factored out a negative 5, then they would both have an x plus 4. And you'd say, oh, wait, there is factors. That goes back to this problem we did over here. If I would have just factored out 1 and I got negative 3c plus 2, I think, oh, well, this is prime because they don't have the same thing in common. But that would have been a human error. I have to factor out a negative, and it makes these the same. That's a human error. So that would have been a false prime. We thought that was prime, but it was not. So got to pay attention to that. When you have the same terms, but they're just opposite signs, that means you need to factor out a negative. And you might think it's a prime because you need to rearrange the terms. And we'll look at one of those that we can rearrange the terms to. So that I understand that that's not necessarily prime. We just think it is. And we can fix that. Factoring trinomials by grouping. All right, let's watch the following pair of binomials be multiplied. So again, we're going to multiply this time t plus 4 times 3t plus 2. Let's make this a little bigger so we can see this better on the screen. T plus 4 times 3t plus 2. So when we multiply t times 3t, we get 3t squared. T times 2 is 2t. 4 times 3t is 12t. And then 4 times 2 is 8. Those middle terms, again, are both like terms. So we can combine them, 2 plus 12. And we get 3t squared plus 14t plus 8. How about if we multiply 2t plus 3 and t minus 7? 2t times t is 2t squared. 2t times negative 7 is negative 14t. 3 times t, 3t. 3 times negative 7, negative 21. And again, the middle terms can combine. Negative 14t and a positive 3t gives us a negative 11t. 4t minus 5, 5t plus 4. 4t times 5t, 20t squared. 4t times 4, 16t. Negative 5 times 5t, negative 25t. And then negative 5 times 4, negative 20. So again, the middle terms combine. Positive 16 and a negative 25 gives us a negative 9t. So what's the difference between these trinomials and ones you factored in the past? All right, let's bring this back down. The leading coefficient, that's the big thing. The leading coefficient here is greater than 1. That's a 20t squared. That's a 2t squared. This is a 3t squared. So when we factor quadratics, we've done that a lot in earlier algebra classes, in Algebra 1, of just like x squared. But when you've got to factor 3x squared or something like that, it's a whole different thing. So let's focus on the 3t squared plus 14t plus 8. You know, if you go back up a step, we had the 2t and the 12t. So let's experiment a little bit with this and see if we can notice a pattern. So I'm going to write this one down. So that's looking at this one right here. When we're multiplying these two together, before we combine the like terms, we had this. We had the 2t and the 12t, and we ended up with that. Let's look at something that's interesting about analyzing what we did. If we take, let's do this. Let's take this first number and the last number. The coefficient of the t squared term and the constant. So that is 3 and an 8. And if we multiply those, 3 times the 8, it's 24. Let's compare that to the numbers we got on the middle terms that are like terms. We got a 2 and a 12. And if we multiply those, it also equals 24. That's not a coincidence. That's a key to helping us factor. Knowing that these need to multiply be the same number. And these need to multiply be the same. So these have to multiply be the same. This and this. And then this combines to be 14t in our final answer because we combine those. But to find this, we would need two numbers that multiply to be the same as these numbers. We're going to play with that, doing some factoring of quadratics. All right, so page 5. Factoring trinomials by grouping. So the first thing we're going to do, though, is going to check this discriminant to see what kind of answers we're going to have on some of these. So let's see. The discriminant is positive. Did they give us? Oh, yeah, there it is. 6x squared minus 11x plus 3. All right, I couldn't find the original problem that was hidden up there in the paragraph. 11x plus 3. Okay, so let's play with this one. Go through these steps on paper, what they want to do with this. The first thing they want to do is, like, if we have a quadratic equation, let's check that discriminant. That's what we had back here. First notes we took, the b squared minus 4ac, went in standard form. So let's see, b squared minus 4ac for this equation. B is negative 11 minus 4 times 6 times 3. Negative 11 times negative 11 is 121. That's 11 squared. Negative 11 squared is the same. 4 times 6 is 24. Times 3 is 72. So this is 121 minus 72, which is 49. 49 is a perfect square. 7 times 7. That tells us there are two real solutions that are rational that we can factor it, because this is a nice, perfect square number. So we want to factor this. But again, we're used to factoring like x squared minus 11x plus 3, something like that we factor. With this 6 out front, we have to rely on what we learned up here. To find how this factors, that middle term, how did we get this 14? We had to have two numbers that multiply to be the same number as these two numbers, but added to be this. So we've got to find the factors of 6 times 3. So we're looking for the factors of 18, because we have to multiply those together like this worked up here and showed us. So the factors of 18 are, and we know it's plus or minus. It could be 1 times 18, or it could be negative 1 times negative 18. Either one would give us 18. Or 2 times 9. And since these add together to be a negative 11, we're going to look at the negative versions of that. 3 times 6. And that's it. Those are the factors of 18. And if we add these together, we'll get negative 19. If we add these together, we'll get negative 11. Add these together, we'll get negative 9. Negative 11. So we want these two numbers. Now that we know the two numbers that multiply together to be 18 and add together, we're going to rewrite this. 6x squared minus 2x minus 9x plus 3. See what I did? I didn't change this equation. I just rewrote it, taking the negative 11 and breaking it into two terms. Negative 2 plus negative 9. Negative 2 minus 9 more. Negative 11. I did that, so now I can factor this by grouping. because I've broken it down where I can simplify it more. 6 and 2, I can pull a 2 out. X squared and x, I can pull an x out. So 6x squared divided by 2x is just a 3x. Negative 2x, factor out 2x, leaves a negative 1. Over here, I've got a negative 9 and a 3, negative 9x and a 3. So if I want 3x minus 1, I need to factor out a negative 3. Negative 9x divided by negative 3 leaves a positive 3x. 3 divided by negative 3 is a negative 1. Ah, look, it's fallen together right here. We've got a 3x minus 1 that we can factor out. What's left when we do that? Factor that out. That leaves just a 2x. Leaves a negative 3. This is the factors of this. Factoring by grouping. We had to rewrite this as two separate terms so that it's like basically doing the opposite of this. We started with the two terms and combined them. This one we start with the combined when we break them out. But to figure out what to break it out is, we have to know that these multiply together to be the same numbers as these multiply together. So I know what these multiply together to be 18. So I had to find two numbers that multiply together to be 18 that would equal this. Negative 2, negative 9. That'd be a positive 18. Factoring by grouping. Generally, this is something you do when you have a coefficient. If it's just x squared, sometimes we don't need to group anything. We can just break it out into the two factors. But if there's a coefficient out there, factoring by grouping is often the simplest way. So that's what they go through here. They go through, look at the discriminant, which told us the term negative 11x should split into negative 9x and negative 2x because we know the 6 times the 3 is the 18. Says, how would you write the given polynomial now with the new terms? That's the negative 9x, negative 2x. So rewriting it as 4 terms. Then you're going to group it. The first 2 terms, you can pull out a 3x. The second 2 terms, you can pull out a negative 1. Oh, they did it. They did it the other way. This is interesting. I should show that as well. Let's look at this as well. If I would have done this differently, because there are 2 ways to do it, and we'll get the same answer. What if, when I wrote these down, I wrote them down in a different order? Same thing, right? I wrote negative 2x minus 9x. This time I wrote negative 9x minus 2x. Does it matter? Sometimes you want to do it just because it's easier to group things together. Because, oh, look, the 6 and the 9, that factors real nicely. But now you got a 2 and a 3, so that doesn't really factor. Up here, I had the 6 and 2, which factor nicely, and the 9 and 3. So that's why I did that. You can pick which one you put first. It doesn't matter. Negative 9 minus 2 is the same as negative 2 minus 9. But this time, when you group it, you've got different groupings than you had up here. So let's see. This is the answer we got last time. What answer are we going to get here? 6x squared minus 9x. Well, there's a 3x that can be factored out of both terms. 6x squared divided by 3x is 2x. Negative 9x divided by 3x is negative 3. What do we have here? We have a negative 2x plus 3. If I recognize, oh, that's the same thing, I just need to factor a negative 1 out. And I've got that 2x minus 3. So now I factor out these. And what's left? 3x minus 1. Look, I got the same answer. They're just, the other one's listed first this time. That's no big deal. If they're being multiplied together, it doesn't matter if I multiply 2 times 3 or 3 times 2. It's the same answer, right? So you can list these in either order, and you'll still get the same answer if you do it correctly. That's a good example. I'm glad they did it differently so I can go back and illustrate that because it does not matter which one you list first. Do it which way you want to group it. Do you want the 6 and 2 together and the 9 and 3, or do you want the 6 and 9 and the 2 and 3? It'll work either way. They just did it the other way, but they still get the same answer. They still get the 3x minus 1 than 2x minus 3. Okay, page 6. Factor completely. More trinomials. Okay, so let's see if there's anything special about this one that we need to do this for any particular reason. Oh, they do this really kind of weird on there, don't they? I don't think there's anything that's really different about this one, so we're going to skip this example. You have this example right here in Buzz if you wanted to go through that, but it works. Yeah, it works the same way. Check the discriminant just to make sure. When you check the discriminant, make sure it's going to work. 2s squared minus 3s. Is that the same one? No, it's a different one. Okay. Oh, this one right here. Factor complete. Let's factor this one. Okay, so if we have this one to factor, the first thing we want to do is check the discriminant, the b squared minus 4ac, because we want to know, are we going to have one solution, two real solutions? Do we got some irrational thing going on, or complex solutions that we need to use the quadratic equation for to solve? That doesn't factor it. So b squared. Well, b is negative 1 minus 4 times 2 times 3. So negative 1 squared is just 1 minus 4 times 2 is 8 times 3 is 24. Oh, look, our discriminant is a negative. What does that say? There's two complex solutions, which means they're imaginary solutions, which means it's not factorable. Not factorable. So not factorable. Put that in our notes. If we try to find something, if we forget to check this and we just start going through our method, oh, okay, I need to multiply 2 times 3. Well, that's 6. What's the factors of 6? It could be 1 times 6 or negative 1 times negative 6, because either one of those would multiply to be 6, or 2 times 3 or negative 2 times negative 3. That would all work. If I add these together, they have to equal negative 1. So that equals 7. Negative 1 times negative plus negative 6 is negative 7. 2 plus 3 is 5. Negative 2 plus negative 3 is negative 5. Look, nothing equals negative 1. None of these factors of 6 will give me this term. Well, that's expected if I know that the discriminant is a negative, because it's not factorable. It's got imaginary solutions. It's not going to be anything that's going to factor into two real factors. So when you get to the situation, go back and think, uh-oh, did I check the discriminant? Maybe there's not any factors. There's no factors, which we see that when we try to find them. But we can save us this work by checking the discriminant. And they go through the whole thing there. So no pair, it's prime. Here's the lesson summary. And then we'll look at a practice problem or two. And then we need to look at the next lesson. We got about 30 minutes, which is more than enough time for the next lesson. Okay, here is the lesson summary for factoring by grouping. There's the questions we had at the beginning. First thing it goes through is the discriminant. When you have ax squared plus bx plus c, you can find the discriminant is b squared minus 4ac. And here are the 4 situations. If the discriminant is 0, perfect square, positive integer, not a perfect square, or a negative number. Steps for factoring polynomials with 4 terms, like you got an x and a y in there. First, greatest common factor. Group the terms, factor the greatest common factor from each little group, and then factor the common binomial. Steps for factoring trinomials by grouping. Factor the greatest common factor. Split the middle term. And we figured out which number to put because we have to multiply the leading coefficient and constant, find the factors that would add to be the middle coefficient, and then rewrite it. Then you do the factor by grouping. All right, they give us some practice problems. Several, which is good. We need several. There's 5 right here on You Try 1 on page 7. Factor each 4-term polynomial by grouping. And this is ones that have x's and y's. So you can go through and try those. You Try 2 has just one constant, but you got to factor it by grouping. 2b squared plus 7b plus 5. I'm going to move on to some of the harder examples, the more trickier ones, perhaps. This has 7 problems right here, and these are ones where factor this and then check your work. They'll give you the answer right there. Factor this, a and a b. Check your work. Let's look at, this one. No, I want that one. I want, what's one I want? Oh, I want this one. Let's do this. So this one, when we look at it right off the bat, like, okay, well, something's got to factor out all these numbers, right? There's a 28, a 68, and a 48. It's just figuring out what factors out of there. Well, it's like with 28, 68, and I know this is a negative, but still, and 48. We know 2 would factor out. That would give us 24, 34, and 24. But these are all still divisible by 2. So where we take out the first 2, we take out another 2, we get 12, we get 17, and we get 12 again. Well, 17 is a prime number. Nothing comes out of 12. So we took 2 2s out. So that tells us if we multiply those together, a 4 should come out of each of these terms. 28 divided by 4 is a 7p squared. 68 divided by 4, this is a minus. So 68 divided by 4 is 17. And 48 divided by 4 is 12. So now we've got an entirely different problem. We factored out a 4 from each of those numbers. P squared p, and there's no variable over here, so we can't factor out anything else. So now we need to take this and break it out to where we can write this as 4 terms so we can do factoring by grouping, because we do have this 7 up front. So 7 times negative 12. We're looking for the factors of negative 84, because that's what 7 times negative 12 is. So I think there's a whole bunch for 84. My goodness, let me see. Did I do this problem yesterday? I did. And notice this is a negative. So one of them is going to be positive, one's going to be negative. The larger one's going to be negative because we want to get a negative 17. The larger one's going to be negative. So it'd be 1 and negative 84, 2 and negative 42. Let's see, does 3 go into that? Yeah, 3 does go into that. That's negative 28. 4 and negative 21. 5 does not go into 84. 6 times what? Not sure 6 goes into that. 7, 8, 9, 10, 11. Okay, that may be it. Oh, wait, 7 times 12? Oh, yeah, 7 and 12. Because that's how we got that. But the bigger one has to be negative because they're going to add together to be a negative number. So this is negative 83. When I add those together, this is negative 40. This is negative 25. 4 times minus 21, negative 17, and negative 5. Hey, that's what we needed. Negative 17. So we can rewrite this. 7p squared. 4 and negative 21. I'm going to put the negative 21 first since I have a 7. Remember, we can write either one first. So let's do negative 21 with the 7 because I'm going to group them. And the 4p can go with the 12. That works nicely. That's one of those where if I write them the other way, I won't see much that can factor out because it's like, but you'll get the same answer either way. 7 and negative 21. That means I can factor out a 3 and I can factor out a p. Oh, I can't factor out a 3. Wait a minute. I can factor out a 7. What did I do? Factor? No. 7 and 21. 7 factors out. 7p out of 7p squared leaves just p. And 7p out of negative 21, that's where the 3 is. And the p factors out. So see that? And then we got a 4p minus 12. So let's factor out a 4. And that leaves p minus 3. And then all of that's being multiplied times 4. So I got p minus 3 in both of these. So I got 4 times p minus 3 times 7p plus 4. That's what it factors down to. 4 times p minus 3 minus 7p plus 4. I'll give you a moment if you're copying that down. So it takes a little bit of work, but we were able to take this big nasty trinomial up here and break it down to its factors, which means then we can solve it. So if we were solving it, we'd set it equal to 0 and say the solutions are p equals 3 and p equals negative 4/7. Because 7p plus 4 equals 0, subtract 4, divide by 7. See, it doesn't have a nice solutions, but one of them is. If you graph that, this is the places where it would cross the x-axis. If you change the p to x's and graph it. But we don't have to solve it right now. We're just factoring. But factoring helps us in our step to solving it. Okay, they got another page of practice problems. They give you lots of practice on this because that's good. 10 problems here. Factor that, and it's one of these two choices. Which one would it be? Would you select that and submit? Incorrect. Oh, I guessed wrong. Then you can go to the next problem, and there's two choices there. So, all right, let's look at the assignment that goes with this first. Then we'll take a look at the second one real quick. Given this trinomial, what is the value of the discriminant? So the first one, all you have to do is find the discriminant. You don't have to solve this one. Given this trinomial, predict the type of solutions. Is it going to have one rational, two irrational? So in other words, you're finding the discriminant again. And then what does the discriminant tell you? Select one of the factors. So you have to factor that, and then one of your factors should be on the screen here. Select one of the factors of this. So you have to factor this, and maybe a factor is here, or maybe they didn't list any of the factors. It's none of the above. And then select one of the factors of this. So each one of those, you're just factoring one. All right, let's look at the sum and difference of cubes, because this is another one of those shortcut things. Look, this is a very short lesson. A perfect cube, I guess we have to be able to recognize that. What a perfect cube. It's a three-dimensional object whose volume is found by multiplying the length, width, and height, right? And they all have to be the same for it to be a perfect cube. So a three-dimensional object where the length, width, and height are not equal is just called a rectangular prism. Like a box could just be a rectangular prism, or it could be a cube. So the first thing we need to know is, can we identify what a perfect cube is? And again, I'll make this a little bigger on our screen. Okay, let's look at these. These are bricks. I'm going to open up the chat real quick. We'll open up the chat so we make sure everyone's still awake. We're almost done. Put this in the chat. Yes or no? Is this a perfect cube? All you got to put is yes or no. Nope, you're quick to say no. Bricks are not perfect cubes. Yeah, we've seen bricks. They are not cubes. They are not the same length, width, and height. They are not. So that's just a rectangular prism. How about dice? Yes, dice are obviously. I should have brought I have dice at home that are not cubes, but they're perfectly fair. They're fair, but they're not cubes. But no, these are cubes because that makes every side the same size and shape. So that way, when you roll it, it's a fair roll as long as they're not weighted. How about like a book? A book can be a rectangular prism when it's closed because it has a height and a width and a length. And yeah, books are not, they're just rectangular prisms. How about this? Oh, these are like jewelry boxes, it looks like. And they appear to be the same height and width and length. So, yes, good job. It is a perfect cube. How about a sugar cube? Okay. Okay. It's got the word cube in the name. A sugar cube is a cube. Yeah. How about like a briefcase? There's a briefcase. Briefcase. All right. So that's the easiest quiz we've had this year, right there. What is a cube? What is not a cube? But that's important to understand when we're doing things with cubes. Is understand what a cube is. So how can sums and differences of cubes be factored? So let's look at this. Sums and differences of cubes. So if we have, they give it to us at t squared minus 4. Remember we had the difference of squares? So we knew, oh, t squared, that's a square. 4 is a square. So that's t minus 2, t plus 2. Great. Shortcut, no work required. Remember we had perfect square trinomials to where if we took the 36 and found the factors, which would be 6 times 6, it's a square number, and we add 6 times 6, if we double it, it's 12t. That's a perfect square trinomial. If we recognize that, we can just immediately write down the factors without any work. And then we had general trinomials that, they're not a perfect square. You have to factor them. You find out 2 and 5 are the factors of 10 that add to be 7, t plus 5 plus that. But what if we have t to the third minus 27? It looks kind of like difference of squares, except for these aren't squares. T to the third is not a square, and negative 27 is not a square, but they are both cubes. It's t times t times t, and negative 3 times negative 3 times negative 3. Oh, wait a minute. So is there a good way to factor this? T times t times t, negative 3 times negative 3, negative 3. So if we had like a cube, if we know the cube roots, like 3 times 3 times 3 is 27, or negative 3 times negative 3 times negative 3 is negative 27. 2 times 2 times 2 is 8. We know we can find the volume of a cube by multiplying those three numbers together. So how does that help us in factoring this? Well, let's look at this video and see how they're going to do that. Because there is a shortcut we're going to learn and put in our notes for factoring this.
The cube root of t cubed is t, and the cube root of negative 27 is negative 3. Now you can tell where the first set of parentheses comes from in the factoring process. What about the trinomial? Where did that come from? Well, take a look at the first and last terms in the trinomial. Do you see any relationship between t and t squared? Do you see a relationship between the cube root negative 3 and 9? You got it! If you square t and square negative 3, you'll get the first and last terms of the trinomial. Finding the middle term is only a little bit tricky. You've probably already figured out that you can multiply negative 3 and t to produce negative 3t. That's close to the middle term, but what about the sign? That's the tricky part. The middle term of the trinomial will always have the opposite sign of the binomial.
The middle term of the trinomial will always be the opposite of the original binomial. Okay, that's good to know. That helps us with our shortcut. So let's take a look at page 2, sums and differences of cubes. So let's write down in our notes the shortcuts, because they're just going to give it straight to us. Just give us the shortcut. Don't have to calculate it another way. They showed us kind of how you get there. So that's why I wrote down their example. They took t to the third minus 27. They said, well, this is t cubed, and this is negative 3 cubed. So if we look at the t and the negative 3, if we put them together, that gives us this binomial. This is their answer, right? If we take this and square it, it gives us the first number. Take this and square it, gives us the last number. And this middle number is when we multiply them together, but the sign has to be the opposite. So for the difference of cubes, difference of cubes, if we have a to the third minus b to the third, here's our shortcut. A to the third minus b to the third. It equals a minus b, just like we did here, a minus b times a squared. This is a minus, and they said the middle term is always the opposite sign. And they just multiply them together. AB plus b squared. That's how that factors. If you notice that you have two cubes being subtracted from each other, this is the shortcut to factor it. Likewise, the sum of cubes is when you have a to the third plus b to the third. So that would be a plus b times a squared minus ab, because they said the middle term is always the opposite of the original, plus b squared. So the important thing to notice is this is always the opposite. That's always the opposite. And this one is always the same. And this is always positive. So same, opposite. That's the only secret to it. Otherwise, it's just AB, A squared, AB, B squared, and the signs just depend on the sign of the original cubes. What signs between there? Same, opposite, and always positive on the last one, regardless. All right, if you've got that in your notes, when you have to factor one of these binomials that are both cubes, you can just write down the answer. There's no work to show. Those problems say show your work. What work? This is a cheat code. I just jumped straight to the answer. Love the cheat codes. Love being able to jump straight to the answer. All right, I'll give you another moment if you're writing that down. Make sure you got that in your notes. It is here in our lesson as well. It is right here at the page 2, right here at the top. A third plus b third is a plus b, a squared minus b, ab plus b squared. Difference, when you have a minus, is a minus b plus ab plus b squared. Perfect. Don't worry, you're not expected to factor these binomials using only your memory. These patterns are given as a guide to follow. There's a guide. You can just use them accordingly. So the only other thing you need to know, here's our last little quiz. And this you can just do, you can do the first letter if you want. Say it's either S, D, or N, or you can say 1, 2, or 3, or A, B, C, whatever, as long as we know what your thoughts are. But is this a sum or difference of cubes? That's about it. A to the third plus 64. Is that a sum of cubes? Is that a difference of cubes? Or is it neither? So put that in the chat. What do you think? The thing you got to figure out is 64 a perfect cube? Well, I'll show you a little cheat thing you got in Buzz. They show us the first 12 perfect cubes right down at the bottom of this page. If you want to put that in your notes or print that out of Buzz or wherever, 1 cube, 2 cube, 3 cube, 4 cube, 5 cube, 6 cube, all the way down to 12 cubed. They have that right here in our lesson. So knowing that 64 is a 4 times 4 times 4 number, it is a cube. That is a sum of cubes. Olivia thought so. How about r to the third minus 25? No, Olivia says that's neither one. R to the third's a cube, but 25 is a square. This is a cube minus a square, so that's not a difference of cubes. That is neither one. 36 plus y to the third. What's your thoughts, anybody? 36 plus y to the third. Is that a sum of cubes? It is a sum, right? There's a plus. That's the only difference between sum and difference. Is this is a plus, this is a subtraction. Saying no, because 36 is not a perfect cube. It's a square. It's a perfect square, but there's not 3 times 3 times 3 or 2 times 2, because see, it goes from 27 to 64, and 36 is in between there. So it is not. How about 125 minus p to the third? 125 minus p to the third. Well, 125, is that on our chart? Oh, it is. Look, it's 5 times 5 times 5. It's right there on that line. And that is a p to the third. So, yep, Olivia's got it. That is a difference of cubes. Oh, what about x third plus 8? Is that neither, or is that a sum? X to the third, we don't have to question that. And 8 is 2 times 2 times 2. That's 2 to the third power. That is a cube. So, as long as you know how to identify that, that'll save you a lot of time in factoring. And again, they do have these right here if you want to put those in your notes, because we don't always have these memorized. We may memorize squares, but we don't often memorize cubes. So factoring, it says factor completely. The only trick about this one is when you look at that 2z to the third plus 250, if you factor out the 2 first, then you recognize it. Oh, wait, this is a sum of cubes because it's z to the third plus 125. Just don't forget the first step to factor out any greatest common factor. You factor a 2 out of that, and then it gets, oh, yeah, that's real easy then. So I can just use the pattern. It's 2 times z plus 5, z squared minus 5z plus 25. All right, and there's another one. Again, you just have to factor out which number comes out of 64 and 729. Well, it says those don't have any common factors, but 64 is a perfect cube and 729 is a perfect cube. It's 9 times 9 times 9. Where do they get that? There it is, 9. Lesson summary. That's all there is on this one. Knowing the patterns. A to the third plus b to the third, a to the third minus b to the third. And remember, factor out a greatest common factor first, because sometimes you won't think there is one of these problems until you factor that out. The next page just has some practice problems for you. 6 of them. Here is the original equation. Here's the factors. You got to match them up. So take this one, write it down, figure out the factors, and then you match it up. Well, if you click on it and then click on its answer, it'll go away if you're correct. All right, let's look at the assignment for this one. Which of the following is a factor of x to the third plus 343? One of these is a factor. which is a factor of 6x to the third plus 6. One of these is a factor. Because you look at that and you think, well, that's not a cube. Well, it is if you factor out a 6 first, because that has a greatest common factor. Then it's just x to the third plus 1 times 6. Which of the following is a factor of 27x to the third plus 512y to the third? Ooh. Which of the following is a factor of x to the 15th minus 64? X to the 15th, is that a cube? Yes, it's x to the 5th times x to the 5th times x to the 5th. Don't forget that. Our rules for exponents means we can take x to the 5th times itself 3 times. And which of the following is a factor of this? So, all right, guys. If you struggle with any of that, come see me Thursday. I'll be in class here. Friday's an A-day, so we won't have class this week on Friday. So if you need help with that, come to class. Some of you have a RTI because your grade's below 70, but there's several of you that don't, that may be struggling with this and need some help. And if so, come see me. I'll be here in class, and then you can leave after you get your help. So, all right, just pay attention to the patterns on this. You can do all of this, the difference of cubes, the sum of cubes. Now we know how to do sum and difference of cubes and squares. We've learned all that good stuff. Factoring by grouping, practice that. You do some of those practice problems. Make sure you got a good feel for that, because we'll be doing that some more during this unit. So, all right, guys, have a fabulous Tuesday, and we'll catch you next time.